All right, so we're talking about section 13.2. Limits and continuity. All right, so our idea of a limit of a function of two variables is similar to our idea of a limit of a function of one variable. What we want for a limit is if we are close to some specific value in the domain, we want that to guarantee us that we're close to some specific value in the range. So let's talk about our definition of a limit with two variables. And this should sound familiar. So we're saying that f of xy is a function of two variables, and z, or L, is a real number. So we say that the limit as xy approaches x0, y0 of f of xy equals L if for every epsilon greater than 0, no matter how small, there exists a delta. Sound familiar? There exists a delta greater than 0 such that, and this is where it's a little different, we get 0 is less than the square root of x minus x0 squared plus y minus y0 squared such that if this quantity is less than delta, this implies that f of xy minus L, absolute value, is less than epsilon. So this quantity x minus x0 squared plus y minus y0 squared square root, what is that quantity? That's a distance formula, right? Right. So we're saying the distance from xy to x0, y0 is less than this number delta. So if we're close, if our point xy is close to x0, y0, very close, that's what this delta means. That's going to guarantee us that our function is close to our limit. So if we get close to some specific value in the domain, that guarantees us that we're close to a specific value in the range. This is how we define, this is our kind of our mathematically rigorous definition of what we mean by close together. And we call this quantity, this x minus x0 squared plus y minus y0 squared less than delta is called the delta neighborhood. The delta neighborhood about x0, y0. Or we call it the open disk. And our disk has radius delta. So we're not going to do epsilon delta proofs with multivariable functions, but I just wanted to, it's kind of important to understand intuitively what the idea of a limit means. The idea of a limit is central. It's like the central idea of calculus. So this idea of a limit and this rigorous definition of a limit is really what makes is kind of the backbone of calculus. The idea of limits is what makes calculus work. So it's important to have an idea of what a limit is telling us. If we're close to some specific value in the domain, that guarantees us that we're close to some specific value in the range. And we can make that specific value, we can get as close as we want. That's what this, for every epsilon greater than 0, that's why I added no matter how small. We can pick how close we want to be in the range, and we can find a value that's in the domain that's close to another specific value that guarantees us that we're as close as we want to be. So let's draw a picture of what this means graphically. So our delta neighborhood or our open disk. So here's our xy plane, and what we're talking about in the xy plane is we have some specific value. Let me draw a circle here for our disk. And here's our x0, y0 in the center of that circle. And this radius is delta. Everything inside that circle is where the square root of x minus x0 squared plus y minus y0 squared is less than delta. So that's our open disk, and we say open because we have a less than sign, so that's why I made the circle dotted. It doesn't include the boundary. So that's our delta neighborhood or our open disk. When we have our x0, y0 in this delta neighborhood, this is what we get in space. So here's our open disk. Here's our open disk in the xy plane. And here's a surface up here above our plane. And I'm going to project this disk up onto the surface. So here would be the projection of the disk up on the surface. And x0, y0 is at the center of this disk. And our radius is delta. So when we're within this disk, that's telling us that our z value, which is the height above the xy plane. So let me go over here. So the highest the function gets us here, the lowest it gets us here. Our limit would be somewhere in this interval. So this would be L, this would be L plus epsilon, and this point down here would be L minus epsilon. So when x and y are within this disk, that guarantees us that our function value is within epsilon units on either side of our limit. This is how we know a limit exists. So that's what our definition is telling us graphically. If we're close to some specific value here, that guarantees us that we're close to some specific value here, and we can make that close be as close as we want. All right, so when we talk about limits of a single variable function, how do we know that a limit didn't exist if we were talking about a single variable function? What told us that limit didn't exist? How do we think about limits? If we had a graph of a function, what told us that our limit wasn't going to exist? So Ryan says this.
Yeah.
So it approaches some undefined value. What was the kind of the big idea that whenever we talk about limits in single variable, there's one thing that we always have to be careful of. Discontinuity, and what's happening to the graph at a discontinuity. You're coming from the right-hand side, and you're coming from the left-hand side. The limits are different. The limits are different on the right-hand side and the left-hand side. So with a single variable function, you have to worry about the limit approaching the limit from the right and the left. In order for the limit to exist, those two limits have to be the same, right? So if they're different, that told you that the limit didn't exist. Well, the multivariable function, the idea of approaching from the right and approaching from the left really doesn't hold. So we can approach x0, y0 along any path, and our limit has to be the same on any path that we approach x0, y0 along in order for our limit to exist. So we need to, when we're thinking about limits of multivariable functions, remember that we can approach this point, this x0, y0, along any path. It's not just from the left and the right, it's from any path. The limits have to be the same on any path. And we'll talk about that, we'll expand on that a little bit more. Now all of our rules for limits that came from single variable functions, so limit of sums, limit of products, limit of quotients, multiplication by a constant, all those rules are exactly the same for multivariable functions. If we're talking about, we're adding two multivariable functions, their limits add. If we're multiplying two multivariable functions, their limits multiply, as long as our limits exist. So a couple of important things that come out of that idea are that limits of polynomial and rational functions with a single variable function, how could we find the limit of a well-behaved function at a particular point? Like a polynomial. Just plug in a value. So same rules hold for multivariable functions. Limits of polynomial and rational functions are found by evaluating the function at the point we're interested in. So polynomials and rational functions are nice. As long as our limit exists, we can say that the limit as xy approaches x0, y0, just writing this in symbolic notation, of f of xy equals f of x0, y0. As long as our limit exists, we can just plug in our value for a rational function or a polynomial. All right, so now we want to expand. We have this idea of how we find a limit, what a limit means for a multivariable function. We want to talk about continuity. And the idea of continuity of a multivariable function, exactly like the idea of continuity of a single variable function. So a single variable function, we're just going to expand this f of xy is continuous at x0, y0. So for a single variable function, what did we want to have for continuity? We had two conditions that we needed to worry about for continuity. What has to happen at x0, y0? We just talked about a limit. So what do we need the limit to be at x0, y? What has to be true about the limit at x0, y0? So if the left limit equals a right limit, or for a multivariable function, if the limit along any path is the same, then we say the limit exists. So we have to have the limit exists. If the limit as xy approaches x0, y0 of f of xy exists, and what was the other thing we wanted to have for continuity? That limit exists and? So we're going to talk about differentiation a little later, but what do we need the limit to be? The function value at x0, y0. And the limit equals f of x0, y0. So we need the limit to exist, and we need the limit to equal the function value at that point. And that tells us when our function is continuous. Same thing for a multivariable function. We need the limit to exist, and we need the limit to be the function value at that particular point. We don't want any kinds of jumps or strange things happening. Our ideas of continuity from single variable functions transfer over to multivariable functions. We can multiply a function by a scalar multiple. That's not going to change our continuity. We can, as long as if we have continuous functions, we can add and subtract continuous functions and get another continuous function. We can multiply continuous functions, get continuous functions. We can find quotients of continuous functions, and we still get a continuous function. Some results of that, transferring what we know about single variable continuity, is that polynomial and rational functions are continuous. And we're going to say they're continuous where they're defined. So all of these ideas from single variable calculus transfer right over to multivariable calculus, and if we have nice functions, polynomial and rational functions, they're continuous where they're defined. We also want to be able to talk about composite functions. And decide about continuity of composite functions. So for composite functions, we're going to say if z, we have some function of f of xy. This function is continuous. And g of z, single variable function, is a continuous function of z. Then the composition of g and f and we can also write it g of f of xy. This composition is continuous. So we can compose continuous functions, and when we do a composition of a multivariable function, we talked about this briefly on Friday. This is a multivariable function, this is a single variable function. This composition is continuous, and our limit as xy approaches x0, y0 of g of f of x, y, is our function evaluated at x0, y0. So compositions, as long as we're composing continuous functions, our composition is continuous as well. So that gives us another tool to work with these multivariable functions. Important thing to remember here is that f of xy is a multivariable function, and g is a single variable function, because I get just a single number out of f of xy. So what this implies is that functions in the form, just to look at some quick examples, functions like e to the x minus y, cosine xy over x squared plus 1, natural log 1 plus x squared y squared. These types of functions are going to be continuous because we're composing continuous functions with other continuous functions. They're going to be continuous where they're defined. All right, so I want to do a few examples for the last few minutes, talking about this idea of limits and continuity. So, questions before we look at some examples. All right, so let's look at, on all of these, we want to talk about continuity. And the limit as x, y approaches 0, 0. And the term that they like to use in our book is discuss the continuity. A lot of students get intimidated by the word discuss. They're just saying, is it continuous? What's the situation with the continuity of this function? Is it continuous everywhere? Is it not continuous at some points? So that's what it means by discuss. So here's our first one, f of xy. E to the xy. So we want to talk about the continuity, and we want the limit as xy approaches 0, 0. Is there anything that's going to make this function discontinuous? This is a composite function. So we're composing the function f of x, y equals xy, and e to the x. This is a composite function. Composite functions are continuous. So it's continuous. It's not undefined anywhere, so it's going to be continuous everywhere. And what's our limit going to be as xy approaches 0, 0? Since it's a composite function, we find our limit. We plug in the values. So if we plug in x and y equals 0, 0, what's our limit? What is it? 1. So because it's a composite function, it's It's continuous where it's defined. This isn't undefined anywhere, and our limit's going to be 1. Let's take a look at what this function looks like. There's e to the xy. And right here in the middle, you can see it raises up a little bit. And so our limit as xy approaches 0, 0, right here in the middle of this grid, is going to be 1. It kind of rises up just a little bit there. So there's a graph of that function. How about f of xy equals x squared over x squared plus 1, y squared plus 1. So this is a rational function. So our rational functions are going to be continuous where they're defined. Is this undefined anywhere? Is our denominator ever going to be 0? No, it's always going to be positive. So this is continuous. And what's our limit going to be as x and y approach 0, 0? Limit's going to be 0. We'll get a 0 in the numerator. And this one, look at that one, there is x squared over x squared plus 1 times y squared plus 1. And as we approach 0, the function is going down here to 0. It's kind of an interesting looking function. All right, how about the natural log of x squared plus y squared? This is a composite function. So it's going to be continuous where it's defined. Where is this composite function not going to be defined?
0.
0, at 0, 0. Natural log of 0 is undefined. So we're going to have a discontinuity at 0, 0 because the natural log does not exist at 0, 0. And how about our limit? Our limit as x and y approach 0, 0. It's undefined, it doesn't exist. Because we're discontinuous, we don't have a limit there. So let's take a look at that one. There's natural log of x squared plus y squared. As we approach 0, 0, if I kept going, we would get just this infinite funnel shape that kept going down, down, down. It's a black hole. So our limit wouldn't exist as we approach 0, 0.
Try and make that function do that.
All right. Let's look at f of xy equals y over x squared plus y squared. Now, this is a rational function, so it should be continuous. It should be continuous where it's defined. So what gives us a problem here? As we're looking at the continuity and the limit as we approach 0, 0. What's that? The bottom is 0. So let's look at our limit along two different paths. So we want to look at the limit as xy approaches 0, 0 of y over x squared plus y squared along y equals 0. I get the limit, and I'm going to drop my bottom here, the limit of 0 over x squared plus 0, which is just going to be 0. So along y equals 0, along the x-axis, my limit is 0. Now let's look at the limit of y over x squared plus y squared along y equals x. So I get the limit of x over x squared plus x squared equals 1 over 2x. And as x approaches 0, our limit approaches infinity. So along two different paths, our limit is different. So along the path y equals 0, I get a limit of 0. Along the path y equals x, our limit is different. Our limit is undefined. So this function is going to be continuous at everywhere except xy equals 0, 0. Because our limit approaches two different values along two different paths. Now let's take a quick look at that graph. So there's a graph of that function. As we go along one line, our limit approaches 0. As we go along the line y equals x, our limit is undefined. That's what's going on with that surface. All right, homework quickly. All right, there you go.